The first model is a one-to-one model. Here, each user-level thread has a kernel-level thread associated with it. When the user process creates a new user-level thread, there is a kernel-level thread that either is created, or if there's available kernel-level thread, then a kernel-level thread is associated with the user-level thread. This means that the operating system can see all of the user-level threads. It understands that the process is multi-threaded, and it also understands what those threads need in terms of synchronization, scheduling, blocking. Since the operating system already supports these mechanisms in order to manage its threads, then the user-level processes can directly benefit from the threading support that's available in the kernel. The downside of this approach is that for every operation, we have to go to the kernel. So we have to pay the cost of a system call, of crossing the user-to-kernel boundary. This, we discussed already, could be expensive. This model also means that since we're relying on the kernel to do the thread level management, synchronization, scheduling, etc., we are limited by the policies that are already supported at the kernel level. So for instance, if the kernel doesn't support a particular scheduling policy, or if the kernel has a limit on the number of threads that can be supported, the process is restricted to operate within those bounds. This basically affects the portability. So if a particular process, a particular application has certain needs about how its threads should be managed, we're limited to running that kind of process only on the kernels that provide exactly that kind of support. The second model is a many-to-one model. Here, all of the user-level threads are supported, are mapped onto a single kernel-level thread. What this means is that at the user level, there is a thread management library that decides which one of the user level thread will be mapped onto the kernel level thread at any given point of time. That user level thread, of course, will run only once the kernel level thread is actually scheduled on the CPU. The benefit of this approach is that it's totally portable. Everything will be done at the user level thread library, scheduling, synchronization, etc., and so we don't rely on any specific kernel level support. Similarly, we are not limited by the specific limits and policies that are available in the kernel. Also, because all of the thread management is done at the user level by the user level threading library, we don't have to make system calls. We don't have to rely on user kernel transitions in order to make decisions regarding scheduling, synchronization, blocking, etc. So this is very different than what we saw in the one-to-one model. The problem with this approach is, however, that the operating system has really no insights into the application needs. It doesn't even know that the process is multi-threaded. What the OS sees is just a kernel-level thread. So the real danger is that when the user-level library schedules one user-level thread onto the kernel-level thread, and let's say this user-level thread makes a request for an I/O operation that's blocking, the kernel-level scheduler will see that the kernel-level thread blocked, and it will basically block the entire process. So the fact that there may be other user-level threads that have useful work to do and the process overall can make some progress, that's hidden from the operating system, from the kernel, and the whole process is forced to wait. This is obviously going to have some implication on performance. Finally, there is the many-to-many model. The many-to-many model allows some user-level threads to be associated with one kernel-level process, others perhaps to have a one-to-one mapping with a process. So it's sort of the best of both worlds. The kernel knows that the process is multi-threaded since it has assigned multiple kernel-level threads to it. And also, if one user-level thread blocks an I/O, and as a result, the kernel-level thread is blocked as well, the process overall will have other kernel-level threads onto which the remaining user-level threads will be scheduled. So the process overall can make progress. The user-level threads may be scheduled onto any of the underlying kernel-level threads, so they're unbound. Or we can have a certain user-level thread that's basically mapped one-to-one permanently onto a kernel-level thread. We call this the bound mapping. The nice thing about this is that if we have certain user-level threads that somehow even the kernel should be able to treat differently to ensure that they have better priority or are more responsive to certain events that are happening in the kernel, we have mechanisms to do this by these bound threads. For instance, if the kernel sees that there is some user input and we have a particular user level thread that's designated to run the user interface for this process, the kernel has a way to immediately schedule the corresponding kernel level thread, as a result of that, also the corresponding user level thread. So this ability to provide this kind of one-to-one permanent mapping in the many-to-many model is another benefit of the model. There are still some cons with this model, and that's in particular because now we require some coordination between the kernel level thread management and the user level thread management, which we didn't see in the other cases. In the one-to-one model, pretty much everything was up to the kernel level manager, and in the many-to-one model, pretty much everything was up to the user level thread manager that's part of the threads library. In the many-to-many model, there's often the case where we require certain coordination between the kernel and user level managers, mostly in order to take advantage of some performance opportunities.